Introducing the automated cornhole scoring system. This product eliminates the problem of losing track of your score while playing cornhole. Our team consisted of 4 members who are all electrical engineering majors. I, Jacob Beckman, did the prototype construction and video editing. Travis Niemerg worked on the programming and vision system. Dalton Wood worked on the color sensor and debugging. And Wyatt Abbott did programming and helped with the debugging of the code. Cornhole is a common game that can be played at tailgates, barbecues, and other social events, indoors and out. This game is comprised of 2 teams playing to a score of 21. The first team to reach 21 wins the game. In distracting social environments, it is difficult to accurately keep track of the score while talking to each other and having a good time. The problem that this cornhole game solves is that it automates the scoring process and leaves participants the sole responsibility of enjoying the game. In cornhole, there are 2 scoring zones that need to be monitored. The board is seen by a vision system, and the teams are awarded 1 point per bag on the board. The hole is monitored by a color sensor, and teams are awarded 3 points per bag that go through the hole. Currently, there are no mass market products like ours that keep score automatically. The scoring options that are mass marketed are shown like the picture on the left, where it's done manually and you have to remember to move the scoring system every time. The picture on the right shows an RFID system that does keep score automatically, but it is not mass produced. The list of specifications shown were established at the beginning of the project. The battery life we were going for is ranging from 10 to 14 hours so that the game is able to be played multiple times without needing to replace the battery. The LCD was also a priority, as it has to be able to display both teams' score and be readable during the game so that teams know what they need to score in order to win. We chose AA alkaline batteries so that the power source, due to the fact that they are widely available, cost-effective, and have a long battery life.
As Jacob mentioned, our approach to automating the cornhole scoring process involved the implementation of a vision system and color sensor. The block diagram shown in the center of the screen displays the layout of our system, and the upper right picture shows the physical dimensions. The vision system implemented was a camera responsible for monitoring the board surface for colored bags, while the color sensor monitored the inside of the hole for bags passing through. Our approach to automating the scoring process for cornhole is unique because our system's portability and its price point, which will be discussed later. Other projects have been done in the past that have automated the scoring process, but RFID was used for both scoring zones, and these projects were not cost-effective options for producing a marketable project. Initially, we planned on using RFID for monitoring the 2 scoring zones, but this approach had to be reevaluated due to financial constraints and range issues. The RFID tag and reader shown in the left picture were the first idea for our project. These modules were cheap, but had very limited range, which would have been resulted in a needing of a sizable array to monitor the entire playing area. Needing to buy so many of these modules would have been expensive as well as impractical due to the amount of I/O pins that would have been used. The longer range, ultra-high frequency readers were beyond our budget. The RFID system was replaced with a camera to cover the board and color sensor for the hole. When the system components were all connected and tested, the 5-volt regulator on the Arduino was being overdrawn when the color sensor, camera, and LCD were all connected to its output, which meant at least one component required a different source of regulated 5 volts for reliable operation. When the camera was detecting objects, the LCD characters dimmed to an unreadable level, which was the result of increased power consumption of the camera for its processing. So a DC to DC buck converter, shown in the right picture, was chosen to power the LCD. By powering the buck converter with the same 9 volts input the Arduino used, the LCD turned on with the Arduino simultaneously, characters maintained the brightness, and the regulator once again was outputting 5 volts. The Arduino Uno microcontroller was chosen for this project because our application required only one program to run through repeatedly. This scoring system just maintains a running tally of each team's score by gathering data from the vision system and color sensor. Since the Arduino Uno only runs one program at a time, it was a fitting choice and was familiar to us since its coding language is fundamentally C++. The Uno also provided our group the advantage of having an available regulated 5-volt output. This was great since the color sensor and the chosen vision system required this regulated 5 volts to operate. Arduino Unos have multiple interfaces that sensors and devices can connect to. In this case, the camera and LCD were on the I2C bus, and the color sensor was on GPIO pins. By having components on the I2C bus, the 4-wire connections left I/O pins open in case buttons or sensors were to be added later. The Pixie 2 camera was chosen due to its versatility. This camera was suitable for our application because parameters like each signature's dynamic color range, detected signature pixel brightness, camera brightness, and frame rate were easily adjusted to provide accurate bag recognition and timing. The Pixie 2 was also advantageous due to its signature detection range that could see the entire playing surface, which was up to 2 feet for our board. In the upper right corner of the screen is a picture showing the output from the camera. Blue is designated Team 2, and the camera can clearly see the entire board and each of Team 2's bags. This camera also had great documentation on how to connect the unit to Arduino for various interfaces, in our case, I2C. But of all the advantages that the Pixie 2 presented for our project, the biggest was the onboard image processing. By having a camera that performed its own image processing, data analysis in the Arduino was simplified and allowed the board to be a standalone unit that did not require a connected computer to operate. Out of the box, the Pixie 2 is connected to a computer via USB, configured in its Piximon configuration software, and is disconnected for independent operation. This ability maintained the portability of regular Cornhole game.
The color sensor that we chose to use to read the bags going through the hole was a TCS 3200. This particular sensor continuously reads the frequency of red, green, and blue waves and converts it to RGB values of anything within roughly an inch range. It came in a pre-built module that has 4 LED lights that help illuminate the area that it is seeing. As shown in the left image, it was mounted directly below the hole so that it will not read bags on the board and only read them when they are dropped through the hole. The general flow of the program that was implemented involves the bags being thrown at the board, and depending on its location, either the color sensor or the camera would relay data to the Arduino. If the bag lands on the board and the camera sees it, relays the color of the bag to the Arduino, and the corresponding team score is incremented by 1. If the color sensor detects, the information is sent to the Arduino, processed, and the corresponding team score is incremented by 3. This is the prototype setup that we decided upon. The top of the board was painted white so that the bags were easier for the camera to pick up, and the inside of the hole was painted black so the color sensor would be able to pick up the bags through the hole easier. The camera was mounted on a steel arm on the back of the board so that it would not interfere with bags being thrown at the board. A hole was cut in the back plate of the board for the LCD displaying the team score. This allowed for the players standing behind the board to view the score. The breadboard and Arduino were mounted inside the back panel under the board so that they are out of the weather and out of sight.
The first scenario we tested was throwing a bag on the board and then knocking it off. This goes to show that the timing of the camera is running at a good rate since it does not increment the first bag because it is knocked off, but it does increment the score of the bag that does stay on the board, whereas the score that's showing is 0 to 1. The next scenario that we completed was throwing bags on the corners of the board. We threw 1 blue and red on both the top and bottom to show that both colors are picked up no matter where they are on the board. This goes to show that the camera has a good vision over the whole board, and as you can see at the end, the score is 2 to 2. For the third scenario, we threw bags off each side of the board. To start, we threw them off on the right side, and as you can see, we hit the board to show that even though they hit the board, the camera still does not pick them up since they did not stay on. And then we continued by throwing a bag of each color on the board to show that the camera is still on and picking up bags that are on the board. This shows that the camera will not pick up bags that are on the side of the board, and it still picks up bags that are on the board. And as you can see at the end, the score is 1 to 1. For the next scenario, we threw 1 bag on top of the other. This shows that the camera will pick up bags that are close in proximity, or even if they're on top of each other. This works well when bags are different colors, but the camera has difficulty doing it whenever the bags are the same colors. At the end, you can see that both bags are picked up and the score is 1 to 1. The final scenario that we have recorded is 1 bag that is on the board being knocked into the hole. This shows that the color sensor and camera can work together. As you can see, the camera does not pick up the one that goes in the hole, and the color sensor does, and at the end you can see that the score is 1 to 3.
The video demonstration shows that most of our scenarios do work out. Unfortunately, the system was not able to pass all testing scenarios. In one instance, 2 bags of the same color landing on top of each other presented issues. As shown in the picture, the camera sees only 1 object even though there are clearly 2 bags. Without modifying the bags, a different system would have to be implemented to differentiate and account for the separate bags. Another scenario in which the system did not meet expectations was when two bags passed by the color sensor one after the other. In this case, the color sensor did not process fast enough that two different colored bags had gone by and ultimately did not relay proper data to the Arduino. Overall, the system passed many of the tests that were demonstrated, but was hindered in some regards. The biggest obstacle was tuning the color sensor to relay proper RGB values based on the ambient light. When we were testing our project, we had to readjust the RGB values set for the color sensor for many different lighting scenarios. The values we received from the sensor changed substantially depending on whether the lighting was natural sunlight, fluorescent lighting, or just your standard light bulb. In some instances, we had sunlight and fluorescent light in a test at the same time, and it would skew the color values. Even shadows cast over the board made a big difference. These varied instances ultimately resulted in the color sensor being functional and accurate only when the sensor was set for a particular lighting condition. At the beginning of the semester, we started with a budget of $400. This may seem a bit expensive since we spent just a little under $200, but at the time of making our budget, we were planning on using RFID to keep track of where the bags went. With the expense of RFID being too great, we changed to a camera and color sensor, which cut the amount we spent by a little over half. The most expensive components on our board are the Pixie 2 camera and Arduino. Even though the Pixie 2 seems expensive when compared to alternative cameras for Arduino, this camera was a great fit for our application and timeline for the project, so the advantages outweigh the cost. Scaling up the production of this project would be difficult. A specialized camera would have to be designed to recognize individual bags instead of purely by color, so it would pick up bags of the same color that are very close or touching each other. Another camera would also need to be implemented so it could monitor another angle in case there's a bag hidden that the camera on the back cannot see. A better color sensor would be needed so more reliable RGB values would be sent to the microcontroller. For the brains of a scaled version of this product, the Arduino Uno would not be the first choice. The Uno has many features that are unused for this project, and having a specific microprocessor that only has needed abilities will lower our cost of production. Some future work that could be done in this project would include enlarging our scaled down 2-foot board to a full-size 4-foot board. In the game of Cornhole, there are generally 2 boards, so integrating Bluetooth for 2-board communication of scores would be a nice addition. Also, the color sensor positioning would need reevaluated. In the position that it is in now, it captures a lot of ambient light, which skews the RGB values that are output to the microcontroller. It would either need relocated to a more secluded location under the board or encased in some kind of shroud that would block the ambient light, or both. Lastly, we would make a box for our components so we could meet our weatherproofing goal of IP54 to protect against dust and splashing water. Overall, this project was a great experience and introduction into computer vision, but would be quite a challenge to have 100% functional in one semester. In our case, we lost a few weeks of work because of scrapping the initial RFID approach and another week in researching new components for our vision system and color sensor. Having parts at the beginning of the semester would be necessary to give more time for troubleshooting and fine-tuning the final product. We would like to thank Dr. Noble, Professor Murin, and Professor Hauer for the lessons taught and helpfulness in developing strategies for approaching this project.